Welcome, everyone. Well, welcome to the exciting world of limits here. And we're going to start by looking at graphical limits. And a good place to do this is to review how do we actually read the graph of a function. So that's what we're going to look at here in this little example. So we have this function y equal to g of x. Here's the graph that's describing this function. And we're going to look at a few different function values. All right, so how do we actually do this? Well, let's look at this equation and let's just flip it around, because really this tells us everything we need to know. Let's write this as g of x equal to y. So when we are trying to evaluate a function, we want to pick out the individual points on that function, on that graph. And the x-coordinate is the input. It's the thing we're plugging in. So the x value, that's the input of our function. And then the y-coordinate for that point, the y value, well, that's the output. That's what we're getting out of our function. So the y value here is the output. So hopefully this is review. I mean, you've probably read graphs of functions before. It's just good to kind of review this, though. All right, so let's look at g of 1. How are we going to do this? Well, we want to find x equals 1 along the horizontal axis. So there it is. And then we kind of look up or down until we see a point that's actually included on our graph. And when I do that, I'm just going to, well, here's x equals 1. Let's read up. There's the point that's on our graph. And I'm just going to enlarge that point just to really emphasize that it's there. So I have this nice filled in point there. And what are the coordinates for that point? Well, the x-coordinate's 1. And to figure out the y-coordinate for that point, I just kind of read over and I have to estimate. So if I do that, I would say maybe like 0.75. You could maybe talk me into 0.8, maybe 0.7. But I'm going to split the difference there, 0.75. So the x-coordinate is the input of our function, and the y-coordinate, that's the output. So in this case, I would say g of 1 is equal to 0.75. All right, let's play that game again, but this time for an input of 4. So again, we find x equals 4 along the horizontal axis. We look up and down until we see a point that's on the graph. And I see that point right there. I'm just going to kind of enlarge it just to show the detail that it's actually there, part of our graph. And then we want to figure out, well, what are the coordinates for that point? So I know my x-coordinate is 4. What's my y-coordinate? Well, I got to read over and kind of estimate. So it looks to be kind of right in the middle. So I'm going to say 2.5. So that means the output of my function, g of 4, is 2.5. All right. Well, now let's get to something a little trickier. What about g of 2? And right there at x equals 2, we have these open dots. So what does this mean? Well, there's kind of two things when we draw a graph. We're either drawing filled in dots or we're drawing open dots. And if we draw a filled in dot, that means that point is actually included on the graph. If we draw an open dot like right here or right here, that means that point is actually not part of the graph of our function. It's not included in the graph. So just like I enlarged this point just to kind of show it and emphasize it, that's all why these appear so much bigger. We're just emphasizing that there's something going on there, and these points are not actually part of the graph of our function. It's kind of like a hole. It's a little point that's missing on our graph. All right, so when we look at x equals 2, again, we want to kind of just scan up and down, and we're looking for a filled in point. So when I do this, Well, that point's not included, so I need to keep looking. And I keep going. This point also not included. So I keep looking, and then nothing. So in this case, we say that g of 2 is undefined. Okay, so good to practice this. Well, this is going to lead us to our idea of limits, right? This kind of interesting behavior here, right at x equals 2. So we're going to introduce the idea of one-sided limits. And I've slightly modified the function. So now this is a brand new function here. The graph looks very similar. The only difference is now I've actually included one of those points. So this is technically a different function because this function actually is defined at x equals 2. But we still have this kind of interesting behavior going on right around x equals 2. And that's what the idea of limits does, is it gives us a way to discuss what's going on around on either side of a point. So let's look at this question. What point does the left side of our curve approach near x equals 2? So we want to go, so we're looking around x equals 2. That's kind of our main focus here. We have this interesting behavior at x equals 2, and we kind of split this up into two sides. There's the left side, and the right side. So we have our left side and then our right side. So we're looking right around x equals 2. And there's the part of the graph that's just a little bit to the left, and then there's the part of the graph that's just a little bit to the right. And we're interested in what's going on either side here. So for this first question, what point does the left side of our curve approach near x equals 2? So we want to imagine standing on over here on the left side. So you want to imagine a little ant or something, or maybe we're standing here. We're standing on the left side, and then we're just going to walk along our curve, and we're going to follow the curve and see where it takes us. But we're going to just stick to this left side. So we don't actually get to x equals 2, but we're going to get closer and closer to x equals 2. And so as we move along the curve, we're getting closer and closer to this point right here. So this point, again, it's not included on the graph, but that's the place, that's the location that we're getting closer and closer to. So the coordinate for that point is 2, 1. So that's the point that we're getting closer and closer to, 2, 1. So you want to think of this as like the location. You want to think of, where are we headed? We're headed to that point. Now, if we play that same game on the right side, now we're standing on the other side of our curve. So we find x equals 2. We go a little bit to the right. And now we're standing over here. And we're going to walk closer and closer. We're going to walk closer and closer to x equals 2. So we're moving closer and closer along the curve this way. And over there, what point are we getting closer and closer to? Well, we're getting closer to that point. Doesn't matter that that point is actually included. That's the location we're getting closer to. And the coordinates for that point are 2, 2. So on the right side, we're getting closer to that point. All right. So what's the mathematical language that we're going to use to discuss this idea of moving a little bit to the left and looking at what happens as you get closer and closer to a value? What about if you go to the right and get closer and closer? Well, the language that we're going to use and the notation that we're going to use is these are our one-sided limits. So we have the left side limit, And the way we indicate the left side is with x approaching a with a little minus there. And then we have the right-sided limit, and that's the language that we use, or the notation that we use, is the limit of our function as x approaches a, but with a little plus. So when we use this notation, you want to think of drawing the number line. Think of the x-axis. Going back up to our graph here. We have our x equals a value, which is the number we're kind of interested in, where something interesting is happening. And we want to approach that number from either side, the left side or the right side. So if we do it from the left side, what's going to happen? Well, we're using x values that are a little bit smaller than 2. So the x values are going to be getting closer to 2, but just take away a little bit, subtract a little bit. And on the right side, what are we doing? We're using x values that are a little bit bigger than 2. So the idea is we're going to be using x values that are getting closer to 2, but just that are slightly bigger, add in a little bit extra. So you want to think of the left-hand limit as just subtract a little. So we're close to 2, but just, in this case, but just subtract a little bit off. And for a right-hand limit, in this case, we're adding a little bit. And so that's the terminology, that's the notation that we're going to use for left and right-sided limits. A left-side limit is if x is approaching some number with values that are slightly smaller. So subtract a little bit. And for a right-side limit, x is approaching a, but with values that are slightly bigger. So add in a little bit. So what would the result be? How could we reformulate this now using this limit notation? Well, in the case of the left side here, we would say our left-hand limit, and our function name is not f, it's g of x. So we're approaching 2 from the left, so I put a little minus there. And in this case, this limit is asking us what's the location, where are you going as x, where is that function going as x gets closer to 2 from the left. So in this case, the location is that y value, so it's 1. And what about the right-sided limit? Well, the way we would write this out is the limit of g of x as x approaches 2 from the right. Again, we're approaching 2, but with values that are just slightly bigger. And we're looking for what's the location? Where are you going? And in this case, the location is this y value of 2. So when we ultimately calculate the limit, it's essentially the y value of the point that you're going to. So when we calculate these limits here, so when we say that the limit of a function f of x is equal to L as x approaches a, either from the right or from the left or from the right, doesn't matter. We do the same kind of process here. This value L, this is the location. This is the y coordinate. Of the point you approach. So this is true for left limits and right limits. So whatever this value of your limit is, that's the y-coordinate of the point that you're approaching. So in this case, if we go back to this example, for the left-hand limit, we're approaching x equals 2 from the left side, so we're using values of x that are getting closer to 2, just slightly smaller. And so we imagine just walking along the curve, and it looks like we're getting closer and closer to this point. Now that point's not included on the actual graph of our function, but that's okay, because we're looking at values that are all slightly to the left. And we're just seeing, where does it look like those points are going? We're following the breadcrumbs there. We're seeing where the trail's taking us, and it looks like it's taking us to that point. And the y-coordinate for that point is 1. So we say the left-hand limit of g of x as x approaches 2 from the left is equal to 1. And then on the right side, again, we're looking at values that are all now slightly bigger. So we're on the right side. And we just kind of follow, again, we follow the breadcrumbs and see where it looks like the curve is taking us as we use x values that are getting closer and closer to 2. So as we use these x values that are getting closer to 2, we kind of follow along the curve, and it looks like we're headed to that point right there. And again, it doesn't actually matter that that point is included or if it wasn't included. The result would be the same. It looks like we're getting closer to this location, and the y-coordinate is 2. All right, so we're going to get a little more practice with this in class, but I think that's a good place to kind of get started here. So try the preparation problem, and we'll see you in class. Bye-bye.